Okay, welcome to the class. So we'll finish our CORESET discussion in this class, and I'll take example use case of PDCCH and PDSCH so that entire top level design is clear in our mind. Okay, so what is left in our CORESET discussion is common search space. Okay, and then this example I'll take. Okay, end-to-end example, and this is basically the references. So this we'll discuss in the next class. Okay, I edited it. This PUCCH chain will come in the next class. Okay, and recap UE. What is UE specific? Each UE has one or more UE specific search spaces configured consisting of multiple core sets. We saw that like this. Okay, right, and these core sets basically evolve with time. That's also we saw. Okay, there's a last slide from the last class. Okay. And UE knows the location of these UE specific search spaces. Okay, we discussed that in great detail. And what are they defined as? They are defined as a function of unique device identity which is allocated to it in the network entry process. And what is CRNTI? I'll correct myself. C stands for cell, R is radio, N is network, T is temporary, I is identifier. Okay. Right, so, and where is this CRNTI used? We remember it is used in scrambling. Okay, this is the only identity a user has as of now. Okay, right, so in each of these search spaces, UE attempts to decode PDCCH using UE specific CRNTI. Okay, right, it fails or passes depends on whether it is able to, the DCI is meant for that user or not, and it will be scrambled accordingly. Right, okay, so if valid PDCCH is found, UE acts accordingly. Okay. Now this is UE specific, okay, and you see that because UE specific CRNTI is used, right? Okay. So it essentially means that the base station knows about this user because it has allocated the CRNTI to this user, right? It has reached that level of network entry. Okay, but when it's like just begin to enter the network and CRNTI is not assigned, how will it enter? Okay, that's what we are going to discuss, and that's where this common search space comes into picture. Okay, and when a user is entering a network, it does not have CRNTI. UE specific search space is not known, correct? Okay, right. So how does it handle? So the 5G defines common search spaces also, which are common to all the users in the network. If it is common to all the users in the network, then it essentially means that it is the data is not scrambled for a user. So it is certain kind of what is called the broadcast information. Okay, right? It is not specific to a user. Okay, but the structure is more or less similar to UE specific search space. Different set of CC is predefined and known to all the devices regardless of their own identity. It makes sense. Okay, right? That the structure should be known to all the users, because if they are trying to enter the network, there should be something known to latch onto, right? You come to IITK and then you find, okay, this is the security section, you first go there, right? Okay, so some kind of anchoring point, and this anchoring point is basically this common search space which is known to all the users, right? So location of and how this common search space provided, okay, well, how will it know? It is not ingrained or it is not programmed in the UE, okay. That information is provided by something called master information block. Okay? You see this, what we are saying here is that we are talking about some other control channels. What control channel we spoke about till now? PDCCH, that is associated with users data, right? When user is trying to enter the network, it's not bothered about data, it's just trying to connect to the network. Okay? So what base station does is it transmits something called MIB, master information block. And what it does is, see, look at this, there is a certain other channel now. It's not PDCCH, it's called PBCH, physical broadcast channel. Okay, it's not specific to a user. That's why it's broadcast. Okay, right? And through that broadcast channel, okay, users should be able to decode this broadcast channel. And in that broadcast channel, this MIB is defined. Okay, and in that MIB, common search spaces are defined. Get the sequence? What am I saying here? Decode this PBCH, okay, right? And this it has to decode. There is a separate procedure. Time permits in this course, I'll tell you what is PBCH and how is it decoded. Okay, that's also blind in the beginning. Okay, that's part of something called the frame acquisition. Okay, it comes later. We'll talk about that. Okay, so let's say it has PBCH. It has decoded PBCH. Then in that PBCH, MIB is defined. In that MIB, common search spaces are defined. Okay, physical broadcast channel. First channel a UE has to decode when it's trying to enter the network. Okay, and the first core set, which is given a name CORESET 0, is defined in this common search space. Okay, there it will latch onto. Okay, and you saw, now you see the CORESET 0 as interlead mapping, not UE specific, because there is nothing base station doesn't even know about this user, how can it make UE specific mapping, right? Okay, so it is interleaved mapping. Okay, why interleaved? Because it is common, correct? Okay, and if it is common, then it should be basically, it should serve the purpose of all the UEs, right? Okay, so what are we trying to say? Interleaved, then channel at one position is good, channel is one part of the band is good, channel of another part of the band is, let's say, bad. So it does that interleaved mapping, so all the users are able to decode it, right? Okay, right. So and typically used interleaved mapping is used CORESET 0, that is one. Okay, and what base station uses is RNTI. Okay, right. It's a broadcast. It's not CRNTI. It's RNTI. Different from what we saw in the last slide. Okay, RNTI allocated during initial access. Okay, to address a UE in CORESET 0. Okay, right. So CORESET 0 is common search space. In that common search space, how will base station address this user using not CRNTI, it is RNTI. Okay, right. And then what follows after CORESET 0 is CORESET 1. Okay, which contains remaining system information. Okay, RMSI. Okay, and additional configuration information from the base station. Okay, right. What are we saying here? PDCCH gets information MIB that has information about CORESET 0. Okay, that is very little information, not the complete information which is required for the user to make the complete network entry. In order to make the complete network entry, it has to find out CORESET 1, okay, which follows CORESET 0. And what does it contain? It contains the remaining system information which the user requires to connect to the network. What is contained in RMSI, we'll come to it later. Okay, so the CORESET 0, move on from CORESET 1, then it is connected to the network, it has gotten CRNTI, then UE specific search space can be defined, and from there onward, whatever we have learned is applicable. Okay, you understand this? Okay, so that's what is common search space. I'm not going into the architecture of this common search space because those restrictions we saw for UE specific search spaces, those restrictions will be there. Aggregation level 1, 2, 4, 8, right? All that remains same. Okay, how is it? Where is it defined? That's what we are talking about. Okay, just to conclude this CORESET part, so search spaces UE specific and common. Okay, both have same structure. Okay, each search space consists of multiple CORESETs. Okay, this is what it was. Okay, each CORESET can have CCE at multiple aggregation level. We have seen that also, like this. This is an example we took. Okay, right, and it changes across users. Can have interleaved or non-interleaved CCE to REG mapping, but not both. And just to conclude, one CCE is how much? 6 REGs. Okay, and one REG contains 12 REs with 3 of them reserved for pilot. We started from here, right? And then we have learned about all this. So this is basically our CORESET design and the restrictions imposed by the standard so that user can decode its PDCCH within the maximum number of attempts. Okay, right? And in order to put everything together, I'm going to take the one example. Okay, and so that all the big picture is clear in our mind. Okay, so what are we saying? Consider a network with hundreds of users. Okay, right. So, and out of these hundreds of users, what base station MAC has done is schedule data for 2 users for transmission in the current slot. Okay, right. So that's how the requirement is. Okay, so what is going to happen? Data for 2 users is going to come from MAC to phi, and what are this user? What is the information transfer block and the DCI for these 2 users? We understand that now. Okay, that's we are beginning from there. The MAC layer. You're not bothered about what happens in the MAC layer and above. Okay, but MAC layer has decided to schedule these 2 users, right? Based on the scheduler sitting here. Okay, so MAC will pass on transfer block and DCI to phi layer for processing. What is the job of phi layer? We know that. Okay, but let's discuss. So you see what format? Let's say okay, DCI format 10 and 00 will be used for downlink and uplink scheduling respectively. Okay, right? Because user needs to send data in the uplink also, and the same DCI can be used for downlink as well as for uplink. Okay, so 10 and 00, why? Because it is no MIMO as of now. Okay, so this format is being used. Okay, right. So what happens here? Okay, so this was that's how this time allocation and domain allocation, we saw that DCI slot n. Okay, right. So how what will this DCI tell? That the data is scheduled in this same slot itself. Okay, that's how we are designing. Okay, so S will be the start symbol, L will be the number of consecutive symbol. The information about the PDSCH is contained in this DCI. Right? These configurations we have studied. Okay. What is this? This is the offset. That offset will be set to 0. Right? So slot offset, slot allocated for PDSCH is determined by n plus k0. So this is slot, nth slot where the data is being transmitted. Okay. So what will happen to k0? K0 will be set to 0. Correct? Okay. The slot offset relative to the slot where DCI was obtained. This is DCI, this is k0. I have not mentioned it, but this is k0. Okay. The student who drew it did not write k0 over there. Forgot to put that over there. Okay. So what is this? For UE1 and 2, what will happen? K0 is 0, S is equal to 9 and L is equal to 4. Some example I am taking. Okay. Then it will start from symbol number 9 and go on for 9, 10, 11, 12. And what is this? G0B uses type 1 frequency domain allocation for both UEs. So what does that mean? Type 1, do you remember what was type 1? It combines starting position and length of resource allocation value into a single value along frequency domain. Type 1, non-interleaved, that's what it is, right? And what is this allocation? This is for PDSCH. That information has to go into this DCI. So it decides that it is going to use this contiguous allocation for these two users, okay? So this information will be encoded in this RIV, which is a part of DCI, right? See, we are creating the information for these users. The DCI information is being created, that's what I am talking about, okay, right. So, and accordingly this data will be mapped onto these PRBs for these users, right. So, if user reads this DCI, it will of course come to know that its data is coming here, the same slot at this offset, right, okay. So, this information is encoded in RIV, a single number you are going to get, right, okay. So, these are the contents of DCI, I am creating DCI content. Okay, based on that PDSCH will be mapped onto same slot at these PRBs. Okay, so this is what I was saying here, resources in frequency domain for UE1 you allocate from PRB3 to PRB20. This was time domain allocation. Time domain allocation, we saw how it was happening. Same slot, start from symbol number 9, goes up to symbol number 12 or 13, right? Okay. So then along frequency, how many PRBs are being allocated from PRB3 to PRB20. This information comes in RIV. This is time domain allocation. You see this allocation, where is it coming from? There is a table defined, right? 16 such configuration were defined in that table. So it will be 4-bit. And this RIV can, depending on what is the size of the bandwidth part, this RIV can have a variable value, okay. But this is one of those 16 allocations, 4-bit for here, okay. And for UE2, it comes from PRB21 to PRB274, some other allocation. That will also be encoded here. Fine, okay. And G0B schedules the user in the uplink using format 01 DCI. Uplink, where should it send, right? Okay, that same DCI has to be, DCI can be used for uplink scheduling also, and that is the format we will use, okay. So time domain allocation in the uplink again, right, because uplink has to happen later. So base station is going to tell the user, please schedule your uplink in this slot, okay. Slot offset, again this is called K2. So UE will schedule its data after K2 slots. If it is like urgent data, K2 can also be 0, right, okay. So that's how it can be configured, okay. The same slot, part of the slot can be used for downlink, other slot part can be used for uplink as well. It can happen. This is the flexibility, but the information is being passed on to the user like this, okay. K2 is the offset, this is the offset relative to the slot where DCI was obtained, okay. So K0, so this is for UE1 and UE2, this should be K2, okay, right. K2 is basically should be 10, not, okay, right, but basically send your uplink data after 10 slot, okay. And this is the location, start at 4 and then goes on for 10 symbols after, okay, right. G0B uses type 1 frequency domain allocation for both UEs. Again PRB3 to PRB20 and PRB21 to 274. Okay, right? They are being used, and how will it be combined? It will be combined using RIV. Right? So look at this DCI. Okay, MCS will have to be defined. New data indicator will have to be defined. Okay, whether it's like old data, old hybrid RQ data or new data. Redundancy version will have to be defined. Time domain resource assignment 4-bit. Frequency domain resource assignment, as I said, right? Okay. RIV, so it depends on the bandwidth part size. So whether it's DCI, this DCI is meant for downlink or uplink 1-bit, correct? Okay. And this is what I have not told you. This I am introducing for the first time. So PDSCH is being scheduled. That has to be acknowledged also back to the base station. When should user indicate that? That is also indicated, and this is a 3-bit indication. And what is this? It indicates ACK-NAC timing with respect to the PDSCH transmission. Okay, what does that mean? Okay, So what is it saying here? Okay, that's where you are receiving your PDSCH, and after K1 slots, please acknowledge whether it was ACK or NACK, and that happens for PUCCH, which I have not taught you still. Because this has to go on the uplink. ACK or NACK has to go on the uplink, right? Okay, but where will it go? That is also defined. That's what I am telling you, right? Okay, so that's how complete control information is being sent, right? So let's continue this. So PUCCH related information, okay. So where PUCCH will be sent, that also has to be indicated. 3 bits for that. Okay. What happens? So now we are clear about what is contained in the DCI, what is the search space. Search space has also been defined. Okay. So DCI is going to come in the search space, PDSCH is going to come in the rest of the space, and that has been defined in this, right, in the DCI. Okay. So let's see. So what happens? DCI has content of DCI are known. It undergoes this processing, correct, right? And what will happen? There are 2 users. This PDCCH transmit chain will run twice for each user. Why? Because what are you scheduling? You are sending 2 DCIs for each user. One for downlink scheduling and another one for uplink scheduling grant. Fine. Get that right? Okay. That's what we said here. Now, I don't want to go back. We will have to go back too much. So what did we say? 2 DCIs, one for downlink and another one for uplink. So this PDCCH chain is going to run for twice for each user. Okay. Then what happens? Okay. Then you have this PDSCH chain. Okay, because you are sending data for 2 users, and this also run twice. Okay, correct. Okay. Now what happens after that? Okay, so this is a CORESET detail that has also been defined. Okay, and it has been defined only at aggregation level 1. We took this example, but putting everything together. So for this user, for these 2 users, they have been defined, the CORESET has been defined at an aggregation level of 1, okay, right, and allocated OFDM symbol are 0, 4 and 8. So this is a CORESET where the DCIs are finally going to be mapped, okay. Duration is 1 OFDM symbol, right, 1 OFDM symbol, period is 10 slot. What am I saying here? This will come after, and then for 9 slot there is nothing, correct, okay, and then mapping is non-interleaved. This mapping is CC to REG mapping is non-interleaved, right? Okay, correct. So everything has been nicely defined. Okay, DCI will be mapped over here. Okay, so then what are we saying? K is basically A plus L, some 60 plus 24, 80 bits. So A is 60 bit. Okay, aggregation level 1, because see, we have been careful. Okay, aggregation level 1. Okay, so how many maximum bits you can send? 108 bits, right? Okay, so DCI cannot be greater than 108. Okay, right, so 60 plus 80, 24, 84 bits, that is K. So DCI for UE1 is being transmitted at symbol 0 at CCE1 and CCE2. Why? Because there are 2 DCIs, remember that. DCI for downlink scheduling and DCI for uplink grant, correct. Similarly, DCI for UE2 is being transmitted at symbol 4 at CCE3 and 4 at these locations, right? Okay, CC3 and 4, okay. So, okay, I am calling this as CC 1, 2, 3, 4. Okay, so this is, if I am calling 3 and 4, so it should be 3 and 4, this should be 1 and 2. Okay, and PDSCH mapping, whereas in UE1 is happening from PRB3 to PRB20, and UE2 it is happening from 21 to 274. Correct? Okay, what will happen? So they'll do this blind decoding. Okay, you know how many decoding attempts they'll have to do if it is coming at CC1 and 2. Right, okay, CC1 one DCI, CC2 another DCI. Okay, so in the first attempt it will get 1 DCI, UE1 will get its DCI, first DCI, UE1 will get second DCI in the second attempt, done. Okay, UE2 will have to make 1, 2, 3, 4, 5, 6, at 7th and 8th attempt it will be able to get its DCI. Once it gets its DCI, it knows where its downlink data is coming and where it has to send its uplink data. So it is ready to receive the downlink data, and basically it is coming in the same slot. Okay, and it will read from where is it going to read? It is going to read from these locations. These locations are clear. It reads that, it knows the MCS, it has the complete information which is required to decode the data. Okay, decodes that, and what happens after that? After so many slots, which has also been indicated to the user, it will either send an ACK or NACK. If it is ACK, process continues. If it is NACK, then also continues, but when let's say hybrid ARQ kicks in either with same RV or different RV, right? Okay. So, and what happened here is, because this is period is 10 slot, correct? Look at this, that this user basically, we have not scheduled other users at all, okay? So other users are going to sleep in the network, they'll save their energy, right? Okay, because you look at this, in this slot, only 2 users are scheduled. Base station is not sending DCIs for another 9 slots after that. Okay, so the users will basically will see. So that's being configured. The core set is being designed, and there are no more core sets coming for another 9 slots. Right, so users don't have to wake up every slot; they can sleep. Fine. Okay, but for these 2 users, they decode their data, send ACK or NACK, and then the whole process continues. Fine, right? So this is how it works. Okay, so at the end of it, what is left for us to understand is basically how this ACK and NACK or some other control information is sent in the PDCCH. Okay, what have we seen till now? We have seen PDCCH. Okay, and the PDCCH DCI can be used for both downlink scheduling as well as for uplink scheduling grant. Okay, there is a one bit which differentiates between downlink scheduling and the uplink scheduling grant. Okay, right? User does that. User searches. There is a search space. It blindly scans this search space, finds out whether DCIs have been transmitted or not. Okay, right? And then if it finds out if the DCI is scheduled for this user, okay, it exactly knows where its data, downlink data is coming. It exactly knows where its uplink data has to go. It exactly knows where ACK or NACK has to go. Okay, right? And all this is defined using DCIs. Okay, so then, but how ACK or NACK is processed, that I have to tell you, because that ACK and NACK are being sent only in the uplink, right? And even that uplink data, okay, right? I have not briefly, what I have said is like PDSCH and PDSCH processing are more or less similar. That's where we have stopped, the kind of chain which we have looked at. Okay, and of course there are certain differences between PDSCH and PDSCH. There are quite a lot of differences. Okay, but at data processing level they are same. After that, when you have to insert pilot signals, at that level there are a lot of differences. Okay, right? So what we are saying, if the user has to send data in the uplink PDSCH, processing, that part of the processing remains same, the data processing. Okay, so it can process data and send it. Okay, right? And so similarly, if it has to send ACK or NACK in the uplink, PDCCH is there. Okay, so we'll see how PDCCH processing is done. That we'll discuss in the next class. But more or less, what we have studied in these classes is how control information is designed, defined, okay, and how it is sent, how UE does blind decoding. Okay, using that, it gets the data. Okay, right? So we stop here. We'll continue discussing this in the next class. Thank you.